This is going to be part 3 of 3 on kinetics, and here we're going to talk about the effect of temperature on reaction rate. So the Arrhenius equation relates rate constant to activation energy. And we'll talk more about this in detail. I should say something about what activation energy really is. If you start out, if we look at an energy diagram, and if we start out with, let's say, reactants here and products here, meaning that we're releasing energy, that we're going downhill, that the products have less energy than the reactants. It doesn't go straight downhill like this. More than likely, you're going to see a diagram that looks like this. There's going to be an energy hump that you have to put in. Even though overall we're going to be going downhill energy-wise, there's still a certain amount of energy that you have to put in. We'll talk more about this later, but that is the activation energy. So we have this equation, K equals A times E raised to the negative E sub A over RT power. EA is the activation energy. R is the gas constant in units of joules per Kelvin mole. K is the rate constant. A is a proportionality constant, and like I said, E sub A is the activation energy. Now, more than likely, you're going to see this equation in this form. Okay, so if two rate constants and two different temperatures are known, we can calculate the activation energy. And that equation is the natural log of the ratio of the rate constants, K2 over K1, is equal to negative E sub A over R times 1 over T2 minus 1 over T1. Now, does this look familiar? You've seen and worked with something very much like this before, the Clausius-Clapeyron equation. And there we were dealing with two different pressures, two different vapor pressures, and two different boiling points. And you were talking about two different rate constants and two different temperatures, but you're doing the same thing. That is that you're relating 2 points along a logarithmic curve. But anyway, you worked with the equation very much like this before. All right, so let's work an example. So let's look at the reaction between methyl iodide and hydriodic acid to form methane and iodine. So I'm going to give you two different temperatures and two different rate constants. So let's say that at 350 Celsius, the rate constant is 3.2 liters per mole per second, and at 400 Celsius, it's 23 liters per mole per second. Okay, so notice the reaction is going faster at a higher temperature. We go up from 350 Celsius to 400 Celsius, and the rate goes up from 3.2 to 23 liters per mole per second. That's a pretty significant increase in rate. So the first thing we want to do is calculate the activation energy. Okay, we use the Arrhenius equation. So to be consistent with our units, that equation incorporates R, negative E sub A over R, and R is in joules per Kelvin mole. So to be consistent with units, we're going to have to convert those temperatures into Kelvin. If you remember how to do that, you simply add 273, right? So 350 Celsius becomes 623 Kelvin, and 400 Celsius becomes 673 Kelvin, right? So we're going to take the natural log of the ratio, K2 over K1. So 23 over 3.2 is negative E sub A over R times 1 over T2 minus 1 over T1. So 1 over 673 minus 1 over 623. Okay, so you take 23 over 3.2, a natural log of that is 1.97, is equal to negative E sub A over R. And then I evaluated the 1 over 673 minus 1 over 623. Okay, and that came out to be minus 1.19 times 10 to the minus 4th. Now the negatives are going to cancel. Negative and times a negative is a positive. That's going to cancel. All right, so solve this for E sub A, and you come out to be 1.38 times 10 to the 5th joules per mole, or 138 kilojoules per mole, which is, okay, that's a reasonable number. Now there's something I want to mention here. It really doesn't matter how you set this up as long as you're consistent. Okay, so I chose to make this K1, which made this T1, and I'd made this K2, which makes this T2, but we could have swapped it around. This could have been K1, and this could have been T1, and this could have been K2, and this could have been T2, and we would have got the same answer. But you can't mix and match. If this is going to be K1, this has to be T1. You can't make this K1 and that T1, right? So it doesn't matter which data set you choose to make K1 and T1 and K2 and T2, as long as you're consistent. As long as this rate goes with this temperature and this rate goes with this temperature. So the next thing we want to do is find the rate at 300 Celsius. Or now that we know what the activation energy is, we could go in and calculate the rate at a different temperature. So K1 is 3.2 liters per mole per second. We'll make T1 623 Kelvin. Okay, that's the same as in the previous problem. And now we're going to solve for K2. We're trying to figure out the rate at a different temperature at 300 Celsius, right? So 300 Celsius, 300 plus 273 is 573 Kelvin. So ln K2 over K1, we know what K1 is. We're solving for K2, is negative E sub A over R. Right now we know what E sub A is, the activation energy. You notice that's going to have to be in joules per mole because R is in joules per Kelvin mole. So I use that as 1.38 times 10 to the 5th times 1 over T2 minus 1 over T1. Okay, so then I evaluated this whole expression, right, and it comes out to be negative 2.32, and we're left with the natural log of the ratio of K2 over 3.2 is equal to negative 2.32. Okay, so you should know how to solve this. We've done it a couple of times now. We got to get rid of the natural log. Okay, got to get rid of the natural logs. We take the inverse natural log of both sides of the equation. So K2 over 3.2 is equal to the inverse natural log, or e raised to this power, to negative 2.32 power, and you get 0.098. And K2 comes out to be 0.31 liters per mole per second. So always ask yourself this question: does your answer make sense? Okay, let's go back and look at when we first started the problem. I gave you a rate at 400 Celsius as being 23, and at 350 Celsius as 3.2, right? And then we dropped it down in this last one. He said we're going to calculate it at 300, okay? So we would expect at 300 it's going to be even lower, that our answer should have been a number less than 3.2, which in fact it was, right? It came out to be 0.31 liters per mole per second. So at 300 it's dropped all the way down to 0.31. Okay, but always check to be sure. Ask yourself, does your answer make sense? So let's talk about reaction mechanisms. Now, this is a question in a previous video I said I was going to address. When we talked about the method of initial rates, we talked about the rate law. And I said that you cannot deduce the rate law from the balanced equation, that you have to go in and calculate it with the method of initial rates. And why is that? Because most reactions occur in multiple steps. Okay, it's not as simple as A slams into B and makes C, for example. It's not as simple as two reactants combined to make a product. So your reaction, what we call the reaction mechanism, is the sequence of individual steps that add to the overall reaction. All right? So you have a series, often you have a series of reactions taking place. An elementary reaction is a simple reaction that describes a single molecular event and the proposed mechanism. In other words, that's one part of your mechanism. And what we call the molecularity is the number of reactant particles that are involved in a single step. Right, so a unimolecular reaction, uni implies one, correct? So that is a reaction that involves the decomposition or rearrangement of a single reactant. So for example, if we looked at the decomposition of ozone, which is O3 decomposing into an oxygen diatomic molecule plus a single oxygen atom, that's just a single reactant. We don't have ozone combining with something else. We just have ozone spontaneously decomposing. There's only one reactant. That's unimolecular. Okay. Now, bimolecular, bi implies two. Bi implies two, correct? So that is one in which two particles react. So if we looked at the reverse of this reaction, or if we looked at not the reverse, but if we looked at O3 combining with ozone combining with this thing, it is the reverse. We looked at an ozone combining with a single oxygen atom to become O2, okay? That is the reverse of this reaction, okay? And that's bimolecular because there's two reactants, okay? This has a single reactant, and this has two reactants. Now, for an elementary reaction, if we know it's elementary, and that is if we know the reaction is occurring in a single step, then we can deduce the rate law from the reaction. All right, so if we have a simple unimolecular reaction where, let's say, some reactant A decomposes to make a product, there's only one reactant here. There's not two reactants, there's only one. A doesn't have to combine with B. A just decomposes. So our rate is going to be proportional to some constant K times the concentration of A. Okay? Now, if we have two A's make a product, if an A has to somehow combine with an A to make a product, then our rate, we're going to have a bimolecular step, and the rate is going to be proportional to the square of the concentration. Okay? And we have an A and a reaction where an A and a B have to come together to make a product. Then again, it's bimolecular. So if the rate is now going to be some constant K times the concentration of A times the concentration of B. Okay? And then last, which we have a termolecular step, where two A's and a B somehow have to combine. Then our rate is going to be equal to some constant K times the concentration of A squared times the concentration of B. That's a termolecular step. You're hardly ever going to see this. It's exceedingly rare where you would have, from a probability standpoint, that you're going to have three molecules that have to come together all at the same time to make a product. Okay. So we said that most reactions occur in multiple steps. Okay, it's not most reactions are not single step. They occur in multiple steps. So what we call the rate determining step is the slowest of the steps in the series. And this will limit how fast the overall reaction can occur. It's like the old saying that a chain is only as strong as its weakest link. Well, a reaction that occurs in multiple steps can only go as fast as the slowest step. All right. So let's look at this reaction. And NO2 combines with a CO. Nitrogen dioxide combines with carbon monoxide, and it gives us nitrogen oxide plus carbon dioxide. So NO2 plus CO makes NO plus CO2. We're transferring an oxygen, basically. So if this reaction occurred in a single step, what would the rate law be? We have two reactants, it would be bimolecular. So if this occurred in a single step, and NO2 would combine directly with the CO. So the rate would be equal to some constant K times the concentration of NO2 times the concentration of CO. But this is not what you observe. If we were to go in and study this reaction by the method of initial rates, what we would find out is that the actual rate law is this, that the rate is equal to some constant K times the concentration of NO2 squared. And the carbon monoxide doesn't even enter it at all, doesn't enter into the rate law at all. So this changing the carbon monoxide concentration has no influence on the rate. Only the NO2 influences the rate. Well, how can this be? The reason is that the reaction occurs in multiple steps. Okay, so how does this reaction happen in actuality? So this is what actually happens. Okay, we have two steps. A NO2 combines with an NO2. Two NO2s combine to make an NO3 and an NO. That's going to be a slow step. Okay, and then in the fast step, the NO3 combines with CO to make your NO2 and CO2. So the slow step is producing the NO3, and once the NO3 is produced, that reacts rather rapidly. Okay, but the reaction can proceed only as fast as the slow step, and that's why we call it the rate limiting step. It doesn't matter how fast this reaction happens. We could increase this CO concentration and we could double it or quadruple it or make it 10 times as high, and it's not going to change the rate. Why? Because no matter how much of this we pump in there, it's going to be sitting there waiting around for more of this to be made from the first step. Okay, so if you have a slow step followed by a fast step, the reaction can only go as fast as the slow step. The second step is going to be sitting there waiting around for that slow reaction to happen. So the actual rate law for the overall reaction is that rate law for the slow step. NO2 combining with the NO2. So the rate law for the overall reaction is the rate is equal to some constant K times the concentration of NO2 squared. Okay, so it's bimolecular in NO2. And that's the overall rate for the overall reaction. Okay. So just a couple of things I want to wrap up here now. One of them is transition state theory and catalysis. So, transition state theory gives you a step-by-step view of what happens during a reaction. So imagine if we had a reaction that's happening and reactant molecules coming together to make a product, and we had some ultra-fast nanosecond camera where we could snap a step-by-step picture as this reaction happens. Okay, so what would we see? The molecules begin to come together, and that's how a reaction happens, is basically by molecules slamming into one another. Okay, the molecules begin to slow down as they approach one another, and as that happens, their kinetic energy is converted into potential energy. Okay, so if the energy is great enough, the molecules form what's called an activated complex, okay? And that's a species with partially broken and partially formed bonds, okay? And the activation energy is the energy required to form the activated complex. Remember I said I'd talk about this a little bit more. All right, so again, like I said, energetically, if you have your reactants here and your products here, okay, your energy diagram will look like this. Like I said, there's that energy hump that you have to get over that for the reaction to happen, even if you're going downhill energy-wise. And like I said, that's your activation energy. Okay. Well, the activated complex is the activation energy is the energy that you have to put in to form the activated complex. Okay, so this is where you have your activated complex. Okay, so one more time, reaction isn't all downhill. Even if it's exothermic, even if you're giving off energy, there's a certain amount of energy that you have to put in to get it started. You have to start breaking the bonds in the reactants. Okay, and that's what the activated complex is. You have to at least partially begin to break down the reactants and form this activated complex. So if the energy, molecules are coming together, they have energy, they have kinetic energy, they come together. Now if that kinetic energy is enough to make it over the hill, form the activated complex, and then it's all downhill. Okay. If the energy is not great enough, well, then what happens? The molecules just bounce off one another and nothing happens. So anyway, that's what activation energy is. It's the energy required to form this activated complex, basically to make it over this energy hump. So the last thing I want to talk about here is catalysts. Okay? So a catalyst, what's a catalyst? A catalyst is a substance that increases the rate of a reaction without being consumed by the reaction. Okay, so a catalyst is not consumed by a reaction. So how does a catalyst work? It makes a reaction go faster, but how does it work? It works by lowering the activation energy for the reaction. Okay, and how does it do that? What it does is it provides an alternate reaction mechanism. An alternate reaction mechanism that has a lower activation energy. Okay, now it speeds up forward as well as reverse reactions. So it does not change the position of an equilibrium. Now we really haven't talked about equilibrium yet, and that's basically the subject of the next chapter, but reactions don't always go to completion. Sometimes a reaction goes part way, like halfway, and then stops, and you wind up with a mixture of reactants and products. If your reaction is in equilibrium, meaning it doesn't go to completion, a catalyst won't change the position of that equilibrium. You might achieve the equilibrium faster, but it won't change the position of the equilibrium. Okay. So last little piece here, we can describe a catalyst as homogeneous or heterogeneous. Homogeneous catalyst exist in the same phase as the reactants, and a heterogeneous catalyst is in a different phase. So let's say, for example, if you're doing a gaseous reaction, let's say, and you're using a platinum catalyst, platinum is a metal. If you're doing a reaction involving gases, let's say using a metallic catalyst, then the catalyst would be present in a different phase. The catalyst is a solid and the reactants are gases. And we'll stop here, and that pretty much wraps up kinetics.